So the lecture today is going to mostly focus on kind of some of the basic theorems of probability functions. But before we start talking about those basic theorems, there are kind of two comments I want to make based on the material we talked about last time. The first comment is this comment about probability as an area. Probability as area. And this is a really, really useful way of thinking about many of these simple probability problems. So what I can do is I can think of my sample space, the set of all possible outcomes, as this area, some area, and an event E is a subset of the sample space, is some sub-area of my box of the sample space. And with this in mind, the probability of my event E, one can think of this as the area of E over the area of S. That is, it's the percentage of the area of S taken up by the area of E, or the percentage of the outcomes, of all possible outcomes, that are in my event. So this is where we get kind of percentages, thinking about probability. It's kind of the percent of the area. And this is a really useful way for thinking about some of these simple probability problems, to draw these Venn diagrams and think about the probability of an event E occurring as the kind of percentage of the area of S taken up by E. And as we get to more complicated, say intersections, unions, etc. of events, you can draw the more complicated Venn diagrams, and you can often arrive at the right answer by looking at the Venn diagram, and then you can work your way there mathematically, precisely with a proof. The second comment I want to make is about infinite unions. And maybe I should be more specific and talk about countable unions. And so we had this axiom of countable additivity last time. And we talked about countable unions. What if I want a finite union? Does the axiom still hold true? Or my theorems and my comments made for infinite unions or countable unions also going to hold for finite unions? And the answer is yes. So the countable additivity axiom said something like the probability of the union of a countable number of events, I can basically distribute the probability across the union. I change the union to a sum, and it's the sum of the probability of the individual events. And this is true as long as the E sub I are disjoint. This isn't exactly how we stated the countable additivity axiom, but it's effectively equivalent to it. It says that the probability of the union of if I take an event and I partition it into some U sub I, then I can calculate the probability of the event as the sum of the probability of the individual E sub I. And another way of saying is that I can just basically distribute the probability of this union, switch the union into a sum as long as the E sub I here are disjoint. That is, they partition something. They partition their union. So what about finite additivity? Is this kind of distributive law going to be true for finite sets? It will be. So if I have a finite collection, say E sub I goes 1 to some n, what I can do is convert this into a new set, let's say B sub I, where I goes 1 to infinity, where B sub I equals E sub I for I goes 1 to n, and B sub I is the empty set for I bigger than n. Notice then that now we've gone from a finite collection of sets to an infinite collection of sets. We basically just tacked on to this a countably infinite number of empty sets. And so that's not really going to change many things. For example, the probability of the union of these E sub I goes 1 to n, is the probability of the union I goes 1 to infinity of the B sub I, because it's just the union of the E sub I, union with a bunch of empty sets, which doesn't change the union. And by countable additivity, as long as, so let's say, if the E sub I are disjoint, the B sub I is certainly going to be disjoint. Tacking on any extra empty sets are disjoint from anything, so that doesn't change the disjointedness. Let's say then the B sub I are disjoint. And let's just move to the lower line here. So our countable additivity axiom says I can write this as the sum of the probability of the individual B sub I. And of course, I can write this as the sum I goes 1 to infinity of, I goes 1 to n of the probability of B sub I plus the sum, let's say I bigger than n probability of B sub I. And all of these are actually going to be empty set. So you could write this as B sub I, but you could equivalently, since B sub I is the empty set, for I bigger than n, that's going to be the empty set. We're going to argue today, and we'll see in a later theorem, that the probability of the empty set is always 0. And so that this whole extra thing is 0. And so this is just the probability of the sum of the B sub I from 1 to n. But over that regime, that's the same thing as the sum of the E sub I. So there's tricks like that work, that take often when we have these results for an infinite or countably infinite number of things, we can extend them to the finite case by just taking the finite number, tacking on an infinite number of empty sets. Doesn't change many of the properties, and the theorem's going to go, we know, hold for the infinite case, and we can do something like a clever proof like this to say, and it also holds for any finite set. This case, in particular, rests on this fact that the probability of the empty set is 0. We haven't shown that, but we're going to show that today. And so the main point of today's lecture is actually going to be to talk about some of the basic theorems of the probability function. So last time we had this definition, which is a probability function, and that the probability function had to satisfy 3 axioms. We call them the Kolmogorov axioms because they were developed by this guy named Kolmogorov in the 1920s. And the Kolmogorov axioms basically codify some of our intuitions about probabilities, or more specifically, they're really talking about codifying our intuitions of measuring things like area. So the third axiom, the first two are believable. Probability should be positive. The probability of something happening should be 1. 100% of the time something should happen. But the third one, this countable additivity axiom, basically is codifying our intuition about measuring areas. And so I said that probability can be thought of as kind of ratios of these areas. And so that third axiom is really about talking about if I take a set E and I break it apart into non-overlapping parts, I can measure the non-overlapping parts, sum them up, and I get a measurement of the whole. And that's actually what the countable additivity axiom is saying. And it's saying that we can actually break that into a countably additive number of parts and do that reconstruction, and everything works out well. Okay, and so given our definition of probability function from last time, and that is it satisfies the Kolmogorov axioms, let's talk about some of the basic properties that you can prove. So we're not going to talk about a specific probability function, but any probability function. We're going to see a whole lot of different types of probability functions in this class. Any probability function will satisfy these. So these are the general, kind of basic probability theorems. So let's write that, basic theorems. That's the theme of today's lecture. So the first simplest basic theorem comes from this observation. Again, more intuition we have. But now we're talking about theorems, not axioms. So our intuition is that if my event E is, let's say, it's raining, then if I want to calculate the probability that it's not raining, not raining, And let's say that the probability of E, that's the probability it's raining, is a third. If I want to calculate, say, the probability it's not raining, so I'm going to abusing notation here. I'm saying probability, quote, it's not raining. What should it be? It should be 2/3, right? Our intuition says, yeah, that should be 2/3. That is, the probability is not raining, we would call the complementary event. It's E complement. And why do we get 2/3? That's 1 minus 1/3. So the basic theorem that we all kind of have intuition about is that the probability of the complement of some event, of that event not happening, so if probability of E is the probability the event happens, the complement, the probability of the complement is the probability that event doesn't happen. The probability the event doesn't happen should be 1 minus the probability that the event does happen. So this is the theorem. And indeed, this is true. So let's prove our intuition here. Let's prove our intuition is that this theorem should be true. And let's show that the Kolmogorov axioms give us enough of our intuition to show that this theorem is true. Proof. So we don't have a lot at this point to work on. All we really have is Kolmogorov axioms, and we're going to build up theorems so we can prove more and more interesting results. But to start, all we have is the Kolmogorov axioms. So let's use those axioms to prove this result. The first thing we're going to notice is that the event S, that is the whole sample space, can always be partitioned as E union E complement. So what's the picture here? Picture here is this is S, I have some event E, and of course, if that's E, then E complement is everything outside of E. And so E union E complement gives me the whole sample space back. Furthermore, not only is the whole sample space the union of E and E complement complement are disjoint. E complement is empty, so E and E complement are disjoint. Using our language. And so from these two facts, our first Kolmogorov axiom 1 says that, axiom 2 says that we have unit measure. The probability of S is 1. And so if I replace S with E union E complement, then I can say that the probability of E union E complement is 1. But E and E complement partition S. And so the second observation is that axiom 3 here, the axiom of, in this case, finite additivity, but of additivity, says that I can break apart, I can distribute this P over a union, switching the union versus sum. So it says I can write P of E union E complement is the probability of E plus the probability of E complement. So that's just basically the additivity axiom. It's not an infinite number of sets, but it's a finite number. And this comes from the fact that E and E complement are disjoint. So let's combine these. And if we combine these two facts, we get that 1 is the probability of the whole sample space, is the probability of E plus the probability of E complement. And so if we rearrange, what do we get? We move the E over, we get the probability of E complement is 1 minus the probability of E. That's the whole proof. Today's theme is simple facts, simple proofs. So that's our first little proof, and basically we could even quantify this thing. We could say this is true for all events. For all events, the probability of the complement is 1 minus the probability of the event. And we proved it using axioms 2 and 3, Kolmogorov second and third axioms. Okay. So that's a nice little fact. There's a real cute little lemma from this. So the lemma, is just a phrase for a term for short little proof. The lemma is called the finite measure lemma. Now here's something we didn't show. The probability of an event E is always less than or equal to 1. So this is true for any event E in my sample space. That's a lemma. That's a theorem. We haven't actually shown that yet. You have intuition that probabilities should be between 0 and 1. We never actually said they had to be. We said they had to be non-negative. We said they had to be real numbers. And we just had this previous theorem that had, we said the probability of the sample space was 1. But our intuition, again, says that it should be less than or equal to 1, right? It shouldn't have more than 100% probability of something happening. So let's show that the Kolmogorov axioms encode enough of our intuition to show that that's true. So this is a cute little lemma that basically uses this previous theorem. And the lemma goes like this. The probability of E complement is 1 minus the probability of E. That uses our kind of complementary theorem we just showed. And E complement is an event. So this is by previous theorem. E complement is an event. And so it has a positive probability. And this is true by axiom 1, non-negativity axiom. So this means that 1 minus probability of E, let's combine these, is bigger than or equal to 0. Hence, probability of E, if I rearrange this, is less than or equal to 1. Done. QED. So that's a nice little theorem. It has a little lemma from our complementary theorem. And the lemma says, so what we have just shown, which is intuition we all have, is that if I look at the probability of any event less than or equal to 1, bigger than or equal to 0. So probability is between 0 and 1. Good, right? Probability is behaving how we think it should at this point. This is all good. But it's interesting that you don't actually need to codify that as an axiom. Kolmogorov's axiom is a kind of basic result of non-negativity, unit measure, and countable additivity. So you see we implicated all 3 of those axioms by this point in order to show this. But you don't need it as any kind of special axiom by itself. So at the beginning of this lecture, we had talked, let's go back up here, we had talked about kind of finite additivity here. And we said, okay, we can basically do this, we have this countable additivity thing, but that also works with finite additivity. You can kind of tack on a bunch of empty sets. Nothing bad is going to happen. And in order to prove that, we had this result here, that the probability of the empty set is 0. The empty set is often called the null event. So the probability that nothing happens is 0. Well, that seems very kind of flip side of our other statement. Axiom 1 or axiom 2 says the probability of something happening must be 1. And we can show, so let's write this down as a theorem, we can show that the probability of the empty set is 0. So again, the proof of this is quite quick. We know by axiom 2 that the probability something happens is 1. We want to show that the probability nothing happens is 0. Of course, we know that the complement of S is the empty set. That is, S less S is the empty set. So S complement maybe looks a bit weird. This is just S less S. That's how we define complement. That's why I am such a stickler about how you define complement. And So let's write this down here. So by a complementary rule, another little theorem is that probability empty set, we can write as the probability is S complement, is 1 minus probability of S, 1 minus 1, zip, 0, zilch, null, goose egg. So that codifies another nice little fact we have, which is that the probability of the empty set should be 0. Maybe not as intuitive. The null event, as it were, is often a little hard to wrap your brain around. But there it is. Okay. So let's continue on with some basic results. And we're going to talk about a basic result here. It's not going to be immediately clear why this is useful, but this is a really kind of useful law of probability. So I'm going to draw out a picture for you, and I'm going to do a kind of picture proof first. And then we're going to formally show that this is true. I'm going to have two events. An event E and some other event, let's call it F. So these are events in my sample space. And what I want to do is I want to calculate the probability of EF complement. So what's EF complement? EF complement is the part of E that doesn't involve F. This is probability of E less F. Same thing, just different notation. So this middle part here is the intersection between E and F. So if I were to do this by areas, I would think that this is going to be the probability of E minus probability of EF, right? It's this area, total area of E minus this little part that overlaps with F. And that indeed is true. That is the theorem. So let's prove it. This is a kind of really useful little probability law that we're going to use a lot. Seems a little bit arbitrary, but if I want to calculate probability of one set with a chunk missing, I can kind of subtract out that chunk. Okay. So the first thing to note is that I can partition E into EF union EF complement. Right? EF is the intersection here, right? As we said, this is E intersect F. And this part here is EF complement. So if I union those together, I get E. Notice that these two things are disjoint. Whenever you see disjoint sets, you should be thinking of our third additivity axiom. That is, if I want to calculate the probability of the disjoint union, I can just add those probabilities. So axiom 3, the additivity axiom, says, aha, if I want to calculate the probability of E, that's the same thing as probabilities EF union EF complement. And now I have a disjoint union. Axiom 3 says I can distribute my probability over. Change the union to a plus. And I get that. And to get the result I want, I'm just going to rearrange. I'll move this EF complement to the other side. Move the EF to the other side. I get probability of EF complement is probability of E minus probability of EF. And that is the result I wanted. All right, so this is, we scroll back up here, this was our theorem. So let's write it in the box and let's write theorem. Fact, that's true. Okay. It seems like an arbitrary theorem, but it's instrumental in proving some of the kind of more intuitive theorems. So let's look at one of them. Here's a more intuitive theorem. I want to calculate the probability E union F. Now you might say that should be the probability of E plus the probability of F. But you'd be wrong. I have not told you that E and F are disjoint. And unless we know E and F are disjoint, I cannot distribute that probability. If they were disjoint, it would be the probability of E plus the probability of F. But if they're not disjoint, the third axiom, the additivity axiom, does not work. The additivity axiom says things must be disjoint. Instead, let's draw a picture here. Two events. So here's my sample space, E, and its larger brother F. If I wanted to calculate the probability of E union F, I'd like to say it's the probability of E, which kind of corresponds to this shaded area, plus the probability of F, which corresponds to this shaded area. The problem is I have now double counted this area here. So that there is double counted. So if I want to calculate the probability of E union F, I could say it's probability of E, this is area of E, area of F, probability of F. But now I've double counted the intersection here. So I've basically double counted E intersect F. So in order to adjust my calculation, I've got to subtract off that intersection because I've double counted it. This is a theorem, and this is true. And this is a nice theorem. So we're going to do a proof of it. Note here, if E and F are disjoint, so E intersect F is empty, then the additivity axiom comes into play again, right? The additivity axiom says that probability of E union F should be probability of E plus the probability of F. Not super legible. Let's try that again. Probability of F. Does our theorem conflict with that? No. If we know that E and F are disjoint, their intersection is empty, and so we would subtract off, according to our theorem, the probability of EF, but we're subtracting off the probability empty set, and that's 0. So we don't violate any rules here. This is a generalization, in some ways, of that additivity, that third axiom of additivity, of countable additivity, or finite additivity. And it generalizes the case, so we'll just write here E and F in this general case here, as we said in the theorem, don't need to be disjoint. That's a nice little generalization of that. Okay, proof. Proof. Let's draw a picture. Here's E, here's F. I'm going to claim that E union F can be written as E union FE complement. And that seems reasonable. E union F is the shaded kind of combination of E and F, which is the area of E, which is that, unioned with the area of F that doesn't include E, so that green area. So that's E or FE complement. And notice that these two things are disjoint. E intersect FE complement is E complement F. The E and E complement cancel to make the empty set, so it's all disjoint. That means we can actually apply our axiom of countable additivity or additivity. So we can actually say that probability E union F is the probability of E, and because they're disjoint, we can say it's plus probability of FE complement. And we now have an expression, so let's scroll back up to our previous lemma, of EF complement or FE complement. FE complement is the probability of F minus the probability of FE complement, that is FE. So that comes from our previous theorem. And that's exactly the result we wanted. Just the probability of E union F is probability E plus probability F minus probability EF. So this first equality here is axiom 3, and this second equality here is the previous result, where we expand FE complement to F minus FE complement complement. That is FE. So this is a nice little theorem that tells us how we can calculate probability of the union of two events even when they're not disjoint. Okay. So let's keep chugging along on some of these basic results. So here is a theorem. And this is another kind of theorem that we have some intuition on. And the intuition is mostly right. So let's consider two events. We have one event E, and then that event E is contained in a bigger event F. Now, if probabilities are like area, so that E is contained in F, and they're both subsets of the sample space, so they're both events, what do you expect the relationship to be between probability of E and probability of F? E is contained in F, and if probabilities are like areas, then we'd expect that the probability of E should be smaller than the probability of F. And indeed, that is true. We have a weak inequality, a non-strict inequality, that E is a subset of F. The probability of E is not bigger than, is less than or equal to the probability of F. And we can prove this using the kind of similar result kind of two theorems ago. So the proof goes like this. If I will look at the probability of FE complement, by axiom 1, that's bigger than or equal to 0. So axiom 1 said that we had this law of countable additivity. I'm sorry, axiom 1 said that we had this law of non-negativity. So any probability of any event is bigger than or equal to 0. FE complement certainly is one such event, so that is bigger than or equal to 0. But we know that we can write FE complement as the probability of F minus the probability of E intersect F. And so going line 1 to 2 there, we use that previous result, and that thing better be bigger than or equal to 0. We can do a little bit of a rearrange here. And this says that the probability of EF less than or equal to the probability of F. Okay. But we should note here, it says note, N-O-T-E, is that E is a subset of F. And as we said in the first lecture, E intersect F. The intersection is just going to be the smaller of the two, is E. So that fact allows us to write the left-hand side as just the probability of E, and so we get our result, that the probability of E is less than or equal to the probability of F. So that's a nice little result. Again, it's codifying some intuition we have, which is that if we have subsets, E is a subset of F, then the probability of E is less than or equal to the probability of F. A sub-event cannot have bigger probability than the event in which it is contained. There's a caveat here about this one, though. Consider the situation where E is a subset of F, but E is not equal to F. So this is what we call a proper subset. improper subset would be if E and F are the same thing. So, question, if E is properly contained in F, is it true that E is strictly less than F? So let's draw two pictures here. So the first one is improper, where we have just one circle, E is F. And the second one is our proper subset. We have F is bigger, and inside it is E. The question here is, if we actually were to know that E is a proper subset of F, can we make a stronger statement? The theorem says, well, we can say it's less than or equal to. But maybe that's only because we don't know if E and F are identical. If we know E and F are not identical, can we make that stricter statement? The probability of E has to be less than the probability of F. The answer, maybe surprisingly, is no. That is not allowed or true. It's possible that E is a proper subset of F, but does not have smaller probability. So this is where our intuition with probability breaks down a little bit. That seems like it shouldn't happen. But consider the situation if you look at, so let's draw one more picture. Here is F, and maybe E takes up like this side of it here. So this is FE complement here. What if probability of FE complement is 0? There's no rule that says that measure doesn't have to be 0. Maybe the probability of FE complement is 0. Then, even if E is a proper subset of F, the probability of E, well, we can show it's going to be equal to the probability of F. Let's show that. Probability of FE complement, we assume that's 0. We can say that this is the probability of F minus probability of EF. So that's using that kind of result from previous. But of course, E is a subset of F. So this is just the probability of E. Just kind of recapitulating our proof here. But now we have a situation where probability of F minus probability of E is 0. So the probability of E is equal to the probability of F. So unfortunately, we can't get any kind of stricter statement. Even if you know the proper subsets, they still could have the same probability. But nicely enough, you know that at least with a weak inequality, it's true. If E is a subset of F, probability of E is less than or equal to, maybe not strictly less than, but less than or equal to F. Okay. So there's kind of two major theorems we want to prove here at the end. And the first one basically is a generalization of our previous theorem. So previously, we had noted that the probability of, let's say, E union F is the probability of E plus the probability of F minus their intersection. And this is true if E and F are disjoint or if they're not disjoint. This is just a generally true theorem. So unlike the third axiom, the axiom of countable additivity, we don't actually need to know that these two things are disjoint. Okay. The question is, can we generalize? Can we generalize this theorem? And we can. This is called something called Bool's inequality. And so Bool's inequality, not an equal sign, we can generalize this fact here to say that the probability of E union F is at most the probability of E plus the probability of F, right? This thing has to be bigger than or equal to 0. So another way of saying this is that the probability of E union F is never bigger than the probability of E plus the probability of F. And Bool's inequality is going to generalize that. So Bool's inequality is going to be a generalization of the statement. Bool's inequality says that if we have some collection, let's say countably infinite, but again, we know that you can do this for the finite case also. If these E sub I are a collection of events, then we can say that the probability of the union of the E sub I is never greater than, never greater than the sum of these E sub I. Now the countably additive axiom, that's axiom Kolmogorov's third axiom, says that if the E sub I are disjoint here, these two things are equal. But more generally, Bool's inequality is talking about the case where we don't actually know if these are disjoint or not. Maybe the E sub I are disjoint, maybe they're not. What we can always say, regardless, is that the probability of the union is never bigger than the sum of the probabilities. Okay, let's look at how to prove this. This one's a little bit of a trick, but not too bad. It's a little more complicated than some of the other theorems we've seen so far. This really is calling for the use of axiom 3. So this calls for axiom 3. That's really what it's calling for here. Is it looks a hell of a lot like axiom 3. Not quite, but it looks a lot. But we can't use axiom 3 straight up here because we don't know if these E sub I are disjoint. Maybe they are, maybe they aren't. So what we want to do is let's replace the E sub I with a set of B sub I that we can use axiom 3 on, with a set of disjoint sequence, we're going to call them B sub I, so that these B sub I preserve the union. So if I look at the union of the E sub I, that is going to be the same as looking at the union of my B sub I. So one will preserve the union. The B sub I are going to be like these mirrored E sub I. They're going to preserve the union. But, importantly, these B sub I are disjoint. So they're like a better version of the E sub I. The E sub I are, they are, but not necessarily disjoint. We can't use axiom 3. So we want to say something about the probability of the union of these E sub I. So let's replace these E sub I with a better version, a set of B sub I. They have the same union, but are better because they're disjoint. How are we going to do this? Well, here's the clever little trick. First of all, we're going to define B sub 1, B sub 1 to be E sub 1. Well, that was an easy first step. Great. B sub 2 is going to be E sub 2, but we're going to subtract out E sub 1. B sub 2 is like E sub 2, but we've removed the E sub 1 part of it. B sub 3 is like E sub 3, but we're going to remove E2, and then we're going to remove E1. To remove the parts of the previous E's. B sub 4 is like E sub 4, but we'll remove E part with E3, we'll move the part with E2, we'll move the part with E1. And we can keep going forever, right? So you can define this more formally, but this is kind of the intuition here. So I'm not going to formally prove this. What I'm going to say is convince yourself. You can prove it at home on Fine Friday evening. Convince yourself the following facts are true. One, that, well, basically, convince yourself 1 and 2 here are true. So let's just talk about intuition for why these are true. Okay, why is the union of the B sub I the same as the union of the E sub I? Well, the B sub i's contain everything in the E sub I. If you have an element in E sub 1, well, it's in B sub 1. If it's in E sub 2, it's in B sub 2. If it's in E sub 3, it's in B sub 3. If it's in E4, it's in B4. So the union, so 1 here is true. The union of the B sub I contains everything in the E sub I. If it's in the union of the E sub I, it's in one of the E sub I. Therefore, it's in that B sub I. Great. The second is that they're disjoint. Why? If you have something in B sub 1, it's not going to be B2, because B2 is basically B1 minus, or E2 minus B1, right? So this is another way of writing this is E2 minus B1. And B3 is basically E3 minus B2. So B2 and 3 are disjoint, and therefore, since 1 and 2 are disjoint, and 2 and 3 are disjoint, we're all good, right? And so forth. And so if it's in, say, B3, it can't be in B4, because B4 is basically E4 minus B3. And it can't be in any of the previous ones because we kind of subtracted those off explicitly. So they're both disjoint, and they have the same union as the E sub I. So they're like this better version of the E sub I. And so ultimately what we wanted to show is that if we look at the probability of this union of these E sub I, we wanted to show eventually, that this is the sum, that this is less than or equal to the sum of the probability of the E sub I. That's called Bool's inequality. So first note that since the union of the E sub I is the same as the union of the B sub I, just replace the union of the E sub I with the union of B sub I. So that equality is true. And these B sub I are disjoint. So axiom 3 says that I can write this as the sum 1 to infinity of the probability of the B sub I. And to make the last point, which is to say that basically we want to claim that this is less than or equal to the sum of the E sub I. If I could show that, then my whole statement is true. The result I want is true. We just have to note that the probability of B sub I is less than or equal to the probability of the corresponding E sub I, because B sub I is like E sub I less, some stuff. So B sub I is E sub I less some stuff. Previous result says that B sub I is, of course, this is another way of saying is B sub I is a subset of E sub I. So the probability of B sub I has to be less than or equal to the probability of B sub I. And so if the probability of each of these things is less than each of these things, we get an inequality, and we get the result we want. And that's called Bool's inequality, which says that the probability for anything, any collection, the probability of the union is less than or equal to the sum of those individual events. So this is nice. It combines axiom 3. It combines our less than or equal to theorem, our subset theorem, in a nice little way. And it's a generalization in some ways of this larger rule here. Generalization so much as it says that the probability of the union is less than or equal to the probability of the sum. Of course, we know from axiom 3, if things are disjoint, they're equal. Okay. Cool. So that's a little nice result called Bool's inequality. It's not the most groundbreaking result in the world. A more useful, kind of practical result, which is super important to know, and is going to be the last result in the lecture today. That's supposed to read theorem. Let's try that again. This is, let's call it event partitioning. Man, I can't spell today. Okay. So let's go back and draw a little picture. So here's our little picture. Two events. Or let's, yeah, sure. Two events, let's say. E and F. And remember how we said that we could write E as E intersect F union E intersect F complement. So this is E intersect F complement, and this is E intersect F. And E is the union of them. So you can always partition an event based on the intersection or not with some other event. A kind of more general every kind of version of this is, okay, so here's my sample space. What I'm going to do is I'm going to partition my sample space into some partition. Let's say C1, C2, C3, C4, C5, C6. Okay, there's my partition. If I take some event E, which I'm going to draw in blue here, I can similarly say, it's supposed to read similarly, I can write E as the kind of union of the intersection of E with each of the kind of parts of the partition. So I can recover E by saying, okay, E intersects C1 is that little thing. So E intersects C1. And I can add on E intersects C2, which is that. E intersects C2. E intersects C3. Union E intersects C3. Union E intersects C4 is this part. Union, on the next line, E intersect C5. Union E intersect C6, right? Which I guess is that part there. So this is with the finite partition, but you can do it with the infinite partition. You can do it kind of with any general partition. Is that if I have a partition of the sample space, some C sub I can partition any event using that same partition by kind of chunking it up and reassembling it based on that partition. And not surprisingly, if kind of probability acts like area, then I can calculate the probability of E by adding together the probability of each of those. So the result also says that I could just kind of say probability of E is the probability of E intersects C1 plus the probability of E intersects C2 plus dot dot dot, plus the probability of E intersects C6, right? You can see that from just looking at the areas in this picture here. But it's true. And so let's prove it. So this is kind of the theorem I'm going to call event partitioning. So let's write it a little more formally. If I have some partition Ci, say potentially accountable partition, is a partition of my sample space, then for any event E, subset of my sample space, the probability, let's write legibly here, probability of E is, I can sum over my partition, I can calculate the probability of E intersect with each of those things in the partition. And I've written here an infinite countable partition, but it's true for a finite, and you can think about how that's true, right? take the finite, tack on an infinite number of empty sets. There you go. Works for the infinite. So the proof is not so bad. Proof of this fact. Basically, we need to show a couple facts. One is that E intersect CI intersect E intersect CJ is empty. So the intersection between, let's call this AI and AJ. So here AI is E intersect CI, AJ is E intersect CJ, for example. The intersection between these is empty. That is, the AI are disjoint. Why is that true? Of course, I can just do more than actually just state it. I can just tell you why it's true. All right, this is ECI, ECJ. That's the same thing as ECI, CJ. This is empty because the C's are partition, and so the whole thing is empty. The second fact is that you have to believe that E is the union, let's say, of these A sub I. That is, it's the union, I goes 1 to infinity, of E, C, I. And that, you can think about how to prove that. I'm not going to go into real formal proof of it, but my picture here I think is fairly convincing of that fact. Is I can break apart E into the intersection with each of the parts of the partition. So I think this picture kind of does justice. You can think about a more formal proof, but it's not necessary, I suppose. And so if we combine these, what do we get? We get that the probability of E is the probability of the union, I guess 1 to infinity, of these A sub I. And now, because these A sub I are disjoint, we can use axiom 3, and we can say this is the sum of the probability of these A sub I, or this is the sum of the probability of E intersect CI. And that's the result we wanted, right? That's the result we stated in the theorem. So this is a super useful result, and we will definitely see this result in the coming lectures. It kind of shows how we can chunk up events based on partitions, and that's a really useful thing to do. Okay, so we're going to stop here for this lecture. We went a little overtime last time. We're going to go a little under time this time. But today what we did is we reviewed some of the basic theorems. First, we started off by saying that, you can think of probabilities. Let's go all the way back to the beginning. You can think of probabilities kind of as areas. We talked about how many of the theorems we state in terms of infinite or countable, say, unions really can be stated in finite also, or imply the finite version. And then we did some basic theorems, some complementary theorems. The probability of the complement is 1 minus the probability of the event. Probabilities have to be between 0 and 1. We had this nice little lemma. Here's our little lemma, which is probability of E minus F is the probability of E minus the probability of EF. So that's another way of remembering this theorem. It's probability of E minus F is probability of E minus the probability of EF. Then we had this general theorem about unions, which is probability of the E union F is probability of E plus probability of F minus the probability of E intersect F. So that's kind of a general case that is kind of implied by axiom, Complementary third axiom. We had the subset theorem, which says that if E is subset of F, the probability of E is less than or equal to the probability of F. We had Bool's inequality, which says that the probability of union is never bigger than the probability of the sum. They're equal if everything's disjoint. And then we had this super useful event partitioning. We'll see how that's useful in the future. which says I can kind of chunk up my probability based on a partition and reassemble it that way. Okay, next lecture we're going to get into some basic counting and some examples, and we'll see a lot of examples of how to use these rules with some basic counting.